So we can take this idea now, and we're starting to see a sort of pattern here, that as we take x values that get very close to one value, we see the function value gets very close to another, and so we can make this jump and say that at the particular x value, the function will be whatever this is getting close to. And we saw the same pattern down here, that as our interval gets infinitely short, our average velocity gets very close to this thing, so we can jump to the conclusion that at that instant of 0.8, the instantaneous velocity is 7.84, and we can generalize that and say that what we're talking about here is instantaneous rates of change. And that's true of velocity is a specific rate of change, and we can say generally that instantaneous rate of change is equal to the limit of the average rates of change. So instantaneous rate of change at a given x coordinate, sorry, that's repetitive, is the limit of the average rates of change around that point. So you take intervals that get very, very close, that get very, very short, starting at the point that you're interested in. Let's see this in a more general example, just a specific algebraic function. So here it says estimate the instantaneous rate of change of the function f of x equals 2x squared plus 1 at x equals 1. So similar idea, this would be a quadratic function. It would look something like that, and we're saying at x equals 1, what's the instantaneous rate of change? And what we're going to talk about more as we go into calculus is this idea that instantaneous rate of change is slope on a function. And so when we talk about instantaneous rate of change, we really mean what's the slope of this line that's tangent to it? In other words, the line that's going in the same direction at that moment, right? So it would have the same rate of change as the function at that moment. Okay, so we're going to apply that logic from the first example we did of taking secants and getting them shorter and shorter. So what we want to do here is think about x values that are very close to but not equal to 1. And so we would have, as x gets close to 1, maybe starting at 1.5, what we want to do is find the average rate of change from 1 to 1.5. So this would be the average rate of change from 1 to 1.5. Again, rate of change just means slope. So I'll put on the left column we're going to plug in x values, and this right column is going to be the average rate of change from 1 to x. So let's actually see what that would be. First of all, let's figure out what the function value is at x equals 1. That'd be 1 squared plus 2 is 2, plus times 2 is 2, plus 1 is 3. Okay, and so then if we think about slope, it's always going to be x, we're going to have some coordinate pair. Our unknown coordinate pair will always have coordinates x, comma 2x squared plus 1. The function value is always going to be given by 2x plus 1 for this function. And so slope would always be y coordinate minus y coordinate, right? This is x and y. X and y, x coordinates 1, y coordinates 3. So we'd always have our slope is going to be our unknown y coordinate minus our known y coordinate, right? Divided by our unknown x coordinate divided by our known x coordinate. So slope would always be, our average rate of change would always be 2x squared plus 1 minus 3 is 2x squared minus 2 divided by x minus 1. Okay, and we're not going to worry about simplifying it or anything, but this is what's going to go into our column right here, right? So instead of just saying average rate of change, that's what it is conceptually, but we know what the actual function is going to be 2x squared minus 2 over x minus 1. And so you want to use your calculator to calculate the corresponding function values. You can use a graphing calculator, or you can use Excel to set up a table. It's very simple to use Excel to set up a table. Let me just show you real quick. Actually, I'll make a separate video to show you that after I finish this one up. So let's just walk through the actual setting up of the table here. So the idea is, again, we want to plug in 1.5 into this slope function to find the average rate of change. When we do plug that in, we would end up getting 5. Okay. And then what we want to do is continue picking x values that get closer and closer to 1, right? We want to find the instantaneous rate of change at 1, so we're going to take intervals that get shorter and shorter, closer and closer to 1. So we could pick 1.1, so we're talking about the interval from 1 to 1.1. The average rate of change on that interval, when you calculate it, will be 4.2. Then we want to get a little bit closer to 1, so say 1.01. And you don't have to pick exactly the same values as me. You can pick whatever values you want that are getting closer and closer to 1. And you do want to increase the decimal places as you get closer, so you know you're getting really, really close to 1. But they don't have to match up exactly what I'm doing. The next question you might have is, how many values do I have to have? And I'm going to say at least 3 before you could possibly have a good sense of what the values are approaching on the right side. So anyhow, 1.01, if I plug that in, I'll find the average rate of change from 1 to 1.01 is 4.02. And now I might be getting a sense that this looks like it's going toward 4, but I need to confirm that with a couple more values. So if I plugged in 1.001, this is again the average rate of change from 1 to 1.001 over 1,000th of a unit. You'd see the average rate of change is 4.002. And now we're getting more and more comfortable with our pattern. If I go even further to a 10,000th of a length interval, I'd have 4.0002. And clearly, as x approaches 1, the average rate of change, that's what this right column is approaching 4. So we will say the instantaneous rate of change of f of x at x equals 1 is 4. Okay, so we basically did 3 problems that are very similar to each other, keep repeating the same process. It can be a little confusing to set up our table here a little bit, but hopefully you can follow those examples, ask questions as you need to get your head around how we set that up. But this is more of a applied context. In the next section, we're just going to more rotely practice finding numerical limits, and that'll kind of be the more important thing in the short term for you guys, is to be able to just follow the logic of, as x gets really close to 1, this function gets really, really close to 4. We're not as concerned about setting up the function right now in the next section, but in this first homework exercise, you'll hopefully be able to match these examples to the exercises and get a good sense of how you can use these limit tables to find instantaneous rates of change. And so there's your introduction to limits and some of the contexts where we would want to use them.